For this section, we're looking at angle bisectors of triangles. This comes from section 5.3 in our book. We start off the section with our first theorem, which is the angle bisector theorem. And that says if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. If we look at our diagram to the right here, our point we're talking about is D. So instead of saying D on the angle bisector, let's just say if AD is an angle bisector, then it is equidistant from the two sides of the angle. Well, DB, DC would be those segments, so then we'll say then BD is congruent to CD, or the lengths are equal. Now, we make those lengths perpendicular to the sides, because remember we measure distance. The shortest distance from a point to a line is that perpendicular, and that's what we use for distance. We're not going to make some random measurement along the side. It's that short perpendicular distance. So, if this is on the angle bisector, wherever it may be, it's going to be equal in BD and CD. Even if we picked another point up here, and then we did perpendicular bisector from there, this one would also be congruent. Any point we go on the perpendicular bisector is going to be equidistant to either side. So, these values are equal in the angle. These values are equal in the sides. We know this is a right angle, so it really opens the opportunity to a variety of different problems we could be solving. To go along with the angle bisector theorem, we have the converse of the angle bisector theorem. And this just goes where we switch the order of the two. So, in this case, we start with equidistant, and they end with bisector. So it says if a point is in the interior of an angle and is equidistant from the sides. So our point is going to be D. So if D is in the interior of angle ABC, and it's equidistant, same idea we used up here, we're going to say BD is congruent to CD. Then we know that AD is an angle bisector. We know that with this occurring, that it's going to bisect the angle and make those two angles congruent, which we could even add to say BAD is congruent to angle CAD, because they are congruent. So, if it's equidistant, now these angles are the same. Up here, we found the segments were the same. Down here, we're finding the angles are the same. So depending on what they give us, we'll be able to solve and find a value if they ask for it. So let's look at a couple examples, how we use each of them, the angle bisector theorem and its converse. Starting with the angle bisector. We have congruent angles. We have the distances. We know we're looking for it to be equidistant, so we set them equal. 3x plus 1 equals x plus 11. I'm going to subtract x from both sides. Get 2x plus 1 equals 11. Subtract 1 from both sides, I get 2x equals 10. So x equals 5. Just to make sure, let's plug our values in. 3 times 5 is 15, plus 1 is 16. 5 plus 11 is 16, so they match, so we know x equals 5 is our answer. So the next one, well, this one actually looks a little bit like the converse, so we're kind of cheating here. Let's move that down here. And we now have this point is equidistant to the sides, so that means these angles need to be the same because it is a bisector. So 7x equals 3x plus 16. I subtract 3x from both sides, I get 4x equals 16, which leaves us with x equals 4. Let's check to make sure. 7 times 4 is 28. 3 times 4 is 12, plus 16 is also 28. They match, so we know x equals 4. Now, down here below we have, for what value of x does P lie on the bisector of angle A? So now we're saying, which value of x are we going to be able to use to have an angle bisector there? Because if these are equal, then we know the angles are congruent, so we have to get to the point where the sides are equal. So, x plus 3 equals 2x minus 1. Subtract x from both sides. 3 equals x minus 1. Add 1 to both sides, we get x equals 4. Check our answer. 4 plus 3 is 7. 2 times 4 is 8. Minus 1 is also 7. So x equals 4 would make them equidistant, which means the angles would be the same. Notice in all of them, whether they're angles or they're sides, either way we're still setting the values equal, really the corresponding values equal, and solving and finding our value. Next we have some practice problems, some examples we can do. Here we have our angle is 27. These are the same. That means it's equidistant. So x equals 15. This uses the original angle bisector theorem. Number 2, this point is equidistant. That means the angles are equal. That's using the converse. Finished. We subtract 3x from both sides. Add 6 to both sides. Get x equals 11. Last one. Angles are the same. We need to find, we know they're equidistant, so 5x equals 6x minus 5. Subtract 6x from both sides. Negative x equals negative 5. That means x equals 5. It's always good to go through and check, make sure our answers fit. If I take 11 and plug it into the second one, we get 33 plus 5 is 38. 4 times 11 is 44. Minus 6 is 38. So that one's good. Third one, take the 5, plug it in. 5 times 5 is 25. 6 times 5 is 30, minus 5 is 25. Those match, so we know our values are correct. Now, we get to the point where we can take not just one angle, but looking at 3 angles within a triangle, and we get that some relationship exists where all of the angle bisectors meet. So we call this theorem the concurrency of angle bisectors of a triangle. And that says the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So we start off at angle, or A. We have angles are congruent. So PA or AP would be our angle bisector. At B, we have it bisects. So BP would be an angle bisector. At C, we have CP as an angle bisector. So let's list those first. If AP, BP, and CP are angle bisectors, well, how does this one finish? If they intersect at a point that is equidistant from the sides. So the point they meet at is P, and if it's equidistant, kind of talks about the theorem we've looked at already, those lengths are all the same. PD, PE, PF. So the angles meet at a point, and that point is equidistant to each side. And when we look at that distance to the side, we still look at the perpendicular because that gives us the shortest measurable distance. So all those values would be the same. Now, we don't just call this the point of concurrency. It has a special name. Whenever we look at angle bisectors, we call it the incenter, is the point they all meet at. So in this case, our incenter would be incenter P. And we know that that point P is equidistant to the sides. Now, if we're talking about being equidistant to the sides, this actually opens up something where we may have to use Pythagorean theorem to solve a problem. If I take a piece out of that triangle, I can copy down and call it triangle PFC. I know I have a right angle. That's actually a right triangle. PF is the distance from the incenter to the side. CP is the distance from the vertex to the incenter. And FC is just that third side. It's that piece. It's a part of the outside of the triangle. But this could actually lead to where we have to solve if they gave us certain values. Well, let's look at an example that does that. So in this one, we're given that N is the incenter of our triangle. We form that by our angle bisectors from each angle meeting at point N. And we need to find ND. So far we know AN is 20. We know AF is 16. Well, I know all these are the same. So ND, NF, they're the same. If I found NF, it would be the same as ND. So let's take that part of our triangle out. I have 20, 16, and NF, and I know it's a right triangle. So if I find NF, I know it's ND, and that would be my answer, but this becomes a right triangle, so we get to use Pythagorean theorem. So Pythagorean theorem tells us that 20 squared equals 16 squared plus NF squared. And if you just want to call this X or A or B or something here, that's fine. We square everything, we get 400 equals 256 plus NF squared. If I subtract 256 from 400, I get 144 equals NF squared. Square root of both sides leaves us with NF equals 12. And we know if NF equals 12, then ND equals 12. Because N is the incenter. So what to expect when you see that incenter? We know the distance from that point to all the sides is equal. We may have to use Pythagorean theorem to work around it, but really the focus you're going to see in this section is going to be